Welcome to this video lecture on process capability. The word capability refers to what a process is able to do. When a process, let's say a filling process, is required to fill bottles with a target volume of 120 mils, not every bottle filled on that process will contain exactly 120 mils. There will be some variation about that value, even if the mean is on target. And so we want to have a way to examine the process and see what the process is able to do. Now, we can measure the process capability by measuring the standard deviation of the measurements that arise in the process. And if the process is normally distributed, well then plus and minus 3 standard deviations describes almost 100% of the values that will arise in the process. So one of the first things we explore when we're looking at process capability is whether the measurements are normal. And well-behaved manufacturing processes are normal. Very often when a histogram displays non-normality, it's because there's some special source of variation present which is unusual. So normality is one of the first checks we perform when we're exploring the capability of a process. But in simple terms, the standard deviation, or plus or minus 3 times the standard deviation, is a measure of the capability of the process. But this is not all. When we measure the standard deviation of the process, we can either measure the standard deviation over the short term or over the long term. Or to use other words, either within a subgroup of data or between subgroups of data collected from different times in the process. Now, as time passes, processes will tend to exhibit more variation because there may be changes in the environment from day to day, or changes in the personnel, or changes in the raw material, or other changes that arise, so that the process may vary in its mean value from day to day or from time to time. So if we collect data over a long period and measure the standard deviation, we will typically get a larger value than if we collect data over a short period of time and measure the standard deviation. Of course, if a process is very well behaved, well then it will behave consistently over a long period of time. And we say that such a process is stable. So stability would mean that the long-term standard deviation is no different than the short-term standard deviation. An analogy for this is, let's say if you view a vehicle from behind. If a vehicle is stationary on a road and you look at the width of the vehicle and you look at the width of the road, you can make a judgment about whether the vehicle is capable of travelling on that road. If the vehicle is wider than the road, then of course there's a problem straight away. If the vehicle is comfortably narrower than the road, then it should be possible for that vehicle to travel on that road. But in this discussion, we're thinking about the vehicle as being stationary. And so the width of the vehicle is simple to measure at a snapshot in time. But when the vehicle begins moving along the road, there may be some side-to-side movement as well. So if we take a video of the vehicle from behind as it travels along the road, the width of the vehicle's path in the video is wider than the width of the vehicle itself. This idea is an analogy to help explain the difference between short-term and long-term variation. So when we have a process, whether it's a manufacturing process or some other process, the way we measure the standard deviation is we take 30 subgroups of size 5. So from 30 different days or 30 different batches, we select a subgroup of 5. So these 5 units arise close together in time. And so when we calculate the standard deviation within a subgroup of 5, we are measuring the within standard deviation, also called the short-term standard deviation. On the other hand, when we calculate the standard deviation based on all of the data, we are calculating the overall standard deviation or the long-term standard deviation. So this this way of collecting 30 subgroups of size 5 is standard practice when we're assessing the capability of a process, and this is a good sample size for this purpose. We don't usually need any more data than this. When we compare the overall standard deviation with the within standard deviation, if the overall exceeds the within standard deviation by more than 10%, that's a clear signal that there is instability in the process, that there is some time-to-time variation. And so if these are different batches, it means we can now check and see if we're setting up the batches differently or if something else is happening to cause variation. When we calculate the within standard deviation, we don't just calculate it within one group of 5 data. We calculate the standard deviation separately within each of the subgroups of 5, which gives us 30 estimates of the within standard deviation. And then we assume that all of these 30 estimates are estimating the same quantity, which is the common within standard deviation. And so we pool all that information together. But the within standard deviation is calculated only by comparing data that arises within the same subgroup. It never compares a number from one subgroup with a number from a different subgroup. That's what the overall standard deviation does. It compares all of the data to get both the inherent random variation within subgroups, and it also includes the time-to-time variation. When we perform a process capability study using Minitab software on our 30 samples of size 5, we get a process capability report as shown here. Now, the first thing we check for is normality. And we look at the histogram, not the curves that are superimposed on the histogram, but we look at the histogram itself, the blue rectangles here, and we see that they do peak in the middle and they do tail off in a fairly symmetric pattern on the two sides. So we conclude that this process is normal. This is the process for filling a bottle with 120 mils of liquid. So it seems that the process is normal, which suggests that perhaps the process is well behaved. Next, we check for stability. In the top left-hand corner, there's some statistics about the process data. And the last two entries in that panel show the standard deviation overall as 1.19 and the standard deviation within as 1.01. Now, in this case, the overall standard deviation is more than 10% greater than the within standard deviation. So we conclude that this process is not stable. The mean fill volumes vary from batch to batch. The two curves that are drawn on the graph represent the short-term and long-term behaviour of the process. The dotted or dashed curve shows the within behaviour. That shows how the process would behave if there was no time-to-time variation. And the solid red curve shows the overall behaviour of the process, which shows us what is actually happening with the performance of this process. The next thing we look at with this process is the centrality. Now, up until this point, we have just allowed the process data to speak to us about the process. We have not inquired for the voice of the customer. We have not mentioned specification limits. But now we consider not only what the process is able to do, but if the process is able to do what the customer requires it to do. So now we introduce the voice of the customer. And the voice of the customer comes in the form of specifications. And you can see we've also drawn on this graph the upper and lower specification limits at 125 mils and 115 mils. So the next question that arises is whether the process is centered. That is the curve in the middle between those two limits. And of course, that's quite easily to see visually, that it's a little bit closer to the lower specification limit compared to the upper specification limit, which means that there's a greater risk of violating the lower spec limit rather than the upper spec limit. We can also see this same information in the sample mean. Up in the top left-hand corner panel, the sample mean is 119.381, whereas it should be 120, so it's a little bit left of centre. And so the centrality compares what the process is able to do with what the process is required to do. And with some processes, it's quite a simple matter to correct that. If the process mean is too small, like with filling bottles, we can increase the fill time or do something else to increase the mean of the process. But with certain other processes, it may not be simple at all to change the mean of the process. The next issue we look at is what we call the capability of the process. Is this process capable of satisfying the customer specifications? And we begin by looking at the short-term variation of the process and see whether that is satisfactory from the perspective of the specifications. So assuming that any instability in the process can be eliminated, then the within standard deviation will apply. And the question is, does plus or minus 3 sigma provide a suitably narrow process that will fit comfortably within the specifications? So we divide the width of the specifications, the upper specification limit minus the lower specification limit. We divide that by 6 sigma, which is the plus or minus 3 sigma. And we need to get a value of at least 1.33 in order for the process to be considered capable. Because this means that the process will fit between the specification limits with a little room to spare. And of course, we need that for small variations that may arise in the process. So this is called CP, the Process Capability Index. C for capability, P for process. So the capability of the process needs to be at least 1.33, or ideally it should be 2, which means the process is twice as wide as what is required. Now, if we go back to our slide, on the right side of our process capability report, you can see the CP value is 1.65, the process within capability. In the final panel on the right hand side, CP is 1.65. That's greater than 1.33. So if this process is centered, it can comfortably satisfy the specification limits. Now, of course, this process is not centered, so we need to also look at the lower side in particular. So to calculate the CPK, the one-sided process capability index, we take the difference between the process mean and the nearest specification limit, which is the lower specification limit in this case, and we divide that by 3 sigma, and that gives us CPK of 1.44, which again is satisfactory. It's bigger than 1.33. So this process, at least in the short term, it's potentially capable. It's capable of satisfying this customer specification. Now, we must pay attention to the overall capability, because the way the process is actually performing is represented by the overall capability in the first part of that panel on the right hand side. So the PP is calculated in the same way as the value for CP, but it's calculated using the overall standard deviation. And there we get a figure of PP is 1.39. So in the long term, assuming that this process can be centered, this process is performing in a way that satisfies the customer specifications. And again, we need to consider the fact that this process is not centered. So if we take the difference between the process mean and the nearest specification limit, which is the lower specification limit, and divide that by 3 times sigma, where sigma is the overall standard deviation, we get a PPK of 1.22, which is less than 1.33. So in fact, this process is not performing. Its overall capability is not satisfactory. Because of the centrality problem and because of the instability problem, this process is not satisfactory. But if these problems could be addressed, then this process would be satisfactory. So the PPK is the most critical measure out of all of those indices in that right-hand panel, because the PPK takes account of the fact that the process may not be centered and takes account of the fact that the process may not be stable. And so if the PPK is satisfactory, usually all of the other indices will be satisfactory. Otherwise, we may need to give attention to this process to improve these measures. Down in the bottom panel, we see the word performance used, and this predicts the parts per million defective from that process. The parts per million that will be defective if it behaves to its best within capability or with its overall performance. So the process performance there is PP, performance of the process, and the one-sided process performance index, PPK, is the key measure. And the parts per million defective, as I mentioned, is at the bottom panel there. So there are some problems about this at the end of section 8A in the textbook. So you're advised to study section 8A of the textbook, and you can read those problems and test yourself with the answers in the back of the textbook.